Hi, Fred. How are you doing?
Doing great. I just got back from the Bermudas on vacation and I'm ready to learn.
Oh, great. You got to go to the Bermudas, huh?
Yeah, I love it there. Lots of sand, lots of sea, and things to do.
That's wonderful. Well, we're going to learn about, I don't think I've ever been to the Bermudas. I'd like to go sometime. Well, I like to do a lot of stuff. So we got elements, compounds in the periodic table.
Haven't we already learned about this stuff?
Yeah, but we didn't learn it to the depth that we need to answer a lot of future problems. So we're going to be working on this today. Sound good?
Yep, sounds good.
All right. Now, we start off looking at and reminding ourselves what is in the nucleus of an atom and what goes around the outside of the nucleus, which all three of these, the electron, proton, and neutron, are called our subatomic particles. Subatomic. What do you think it means, Fred?
Smaller than the atom?
That's right. Smaller than an atom. We got these proton, neutron. They are in the nucleus, and the electrons go around the outside. We already kind of know that. But we've never really talked about the mass of these, the protons and neutrons. And what we're seeing here is the proton and neutron's mass are about the same, but the electron is about 1,000th the mass. So it takes about more than 1,000 electrons to make the mass of a proton or neutron. So when we talk about the mass of an atom in the future here, it's the mass of the contributing protons and neutrons. It's not the electrons. All right. So we've also talked about the charge of the electron, negative, proton, positive, neutron, no charge. All right. We talked about our elemental symbols, and we use our periodic table. Now, if you haven't printed out a periodic table yet from the home page of the course, you have to do that now. You have to print out a periodic table, push pause, and go print it out, because you're going to need that periodic table, and you're going to need to bring it to class or anytime we're talking about anything, always, because that's how we're going to familiarize ourselves with the periodic table, and it's very essential to have. On the back of your periodic table, there is some, there are some tables, all right? Here are the tables on the back of the periodic table and that you're going to print out, and I need you to have those available as well. So, yeah. Now, back to this. Each element has a letter, sometimes a couple letters, right? And each element, also, we can know how many protons there are on the elements. For example, nitrogen. Do you know how many protons nitrogen has, Fred?
7.
That's right, the 7 up here, right? Sulfur, how many protons?
16.
That's right. So the number that's to the top left of our periodic table element there is the number of protons, okay? Now, if I am just writing down element C, carbon here, I can also write to the bottom left the number that will tell people the number of protons that atom has. So in a way, it's redundant for people who already have the periodic table, because they can see, oh, it's carbon. They can look for themselves. So the 6 isn't helpful. But sometimes you'll see that, not very often anymore because of the familiarity that people have. But I can also, to the top left, like this one here, write the sum of the neutrons and protons in an atom. So, for example, if I write carbon 12, and we want to call it carbon 6, we're not, when we call it an element, it's the name of the element and then some number. The number is the sum of the protons and neutrons. Okay? This is just the protons down here, but the top left number, the superscript to the left, is the sum of the protons and neutrons. Okay? In our periodic table, down at the bottom of each element, down at the bottom of each element, nickel, 58.69, so it's kind of small there, but that number, oxygen here, 15.9994, that number is the mass number. Now, it's not the mass of every single atom of oxygen, or this 12.011 is not the mass of every atom of carbon. It's the mass of the average atom of carbon. So different atoms of carbon have different masses because they have different number of neutrons. They don't have a different number of protons. If they're carbon, they have the same number of protons, but they can have different number of neutrons, which will give them a different mass. So we have carbon 12, yep, but there also exists carbon 13 and carbon 14, all right? So essentially, these are all with a 6 down here, 6 protons, of course, but they differ in the number of neutrons, and we call this, when different number of protons and neutrons, isotopes. Isotopes, okay? So this is a single isotope, but generally it's an isotope of something else, right? So it's kind of hard to say one thing is an isotope because it's an isotope of another element with a different, same number of protons, but different number of neutrons, okay? So we have, again, here's an example, iron 55 we call it. Again, we name it, the number, if we're going to give it a number, we name it based on its mass number, which tells us protons and neutrons. So can you look at this iron here and tell me how many protons it has?
Can you show me the periodic table?
Yeah, I could, but remember, what is this number down here?
Oh, that's the number of protons. So iron has 26.
Very good. So how would we identify the number of neutrons in this specific atom of iron?
You would take 55, which is the sum of the protons and the neutrons, and subtract the 26.
Very good. And that would be 29, right? So this species here has 26 protons, 29 neutrons, all right? 55 is the mass altogether. Okay, very good. So let's see if you think you can fill out this table here, all right? Folks at home, why don't you guys push pause, go ahead and fill out this table, and then Fred will help you out. All right, everybody have a chance, hopefully. Fred, what do you think?
Cobalt, let's see, I see it down there, it's number 27, so that's 27 protons.
Very good. And how many neutrons?
60 minus the 27, that's 33.
Very good. How about electrons?
I don't know how many electrons.
All right. Well, we didn't really talk about that, did we?
No.
Well, the number of electrons will be the same as the number of protons for an atom that doesn't have a charge on it. Okay? So does this atom have a charge on it?
What will a charge look like?
Well, if it has a charge, it'll be something like this. Let me move my periodic table. If I wanted to show this carbon 14 with a positive charge, it would be right there. If I wanted to show this carbon 13 with a negative charge, it would be right there. Okay? So, how many electrons would this species have?
27 electrons.
Very good. Very good job. So, how about bromine 81? How many protons would bromine 81 have?
Yeah, I can't see. Bromine is 35.
Very good. Neutrons?
What's 81 minus 35?
I'll put it in my calculator here. 46.
Okay, 46 neutrons. And then 35 electrons, because there's no charge on there, is there?
No, there's not. So yes, that's right. The same number, 35 electrons. So how about this one? What species then goes here?
29. 29 is copper.
Good. So what would we call it? Copper 29?
Yeah, copper 29.
Are you sure?
Doesn't it have 29 protons?
Yeah, but we don't call it the number of protons. That's redundant, right? It's like saying the same thing. We use the number of protons plus neutrons to name it.
Oh, yeah, okay. So that would be 65. So copper 65?
Very good. Copper 65. Excellent job. Here's another one. Folks at home, take a shot at this one. Let's see if you get it. Bring out the periodic table. What do you think, Fred?
Lead. Lead is element 82.
Very good. This 82 helped us out there as well, right? So 206.
Well, if it has 82 protons, the only one that it can be is D, because it has to have 82 electrons. There's no charge.
Very good. And then the 206 minus the 82 is where we get the 124. Okay? How many neutrons are there here?
I got it. You want me to tell you?
Give the folks at home a chance. Okay, everybody at home? Push pause if you don't got it yet. What's the answer?
It's 26.
Very good. 26 is also the number of protons, but in iron 52, it's the number of neutrons as well. Very good. So, if naturally occurring element, a naturally occurring element, in this specific case, we're talking about chlorine, if a naturally occurring element contains only two different kind of isotopes, and let's say 75.77% of the one are chlorine 35, and the rest are chlorine 37, okay? Then, and if chlorine 35 has a mass of 34.98689, okay, so that's the exact mass of our chlorine 35, and chlorine 37 has an exact mass of 36.9659, we can calculate the average atomic mass of chlorine. So what do you think? What's the average atomic mass?
Well, wouldn't you just take those two masses, 34.9689 and 36.9659, and take their average?
Well, you would do that if there was only two atoms and one had one mass and one had the other. Or maybe if there were 100 atoms and half had that mass and half had the other. But in this case, it's not a half and half, not a 50-50 ratio. It's 75.77 has the mass of 35, while only 24% has the mass of 37. Okay, so what would we do?
I'm not sure I know how to set this up.
Okay, well, if we set it up like this, let's see if this would make any sense. 34.9689, that's the 35 mass. I know out of 100 of my atoms that I pull out of this, I'm going to draw something, a little picture over here. Tell me if you can tell what I'm drawing, okay, Fred?
Okay.
Here we go. Ready?
Circle, little circle inside. Looks like a upside down hat or something.
That's right, it's a hat. A hat.
Okay, so what?
Well, if I have inside this hat 35s and 37s, and I want to know the average, and I pull out 100 of them and make a list of the number of 37s, or the masses of all of them, right? Right? Then I can add them all together and divide by however many I pulled out. If I did that 100 times, then I would get 75 of those 100 being mass of 35, and 24.2, 35.7 here, and 24.2 having a mass of the 37. So I could add all those numbers up, but it would take a long time on my calculator to add up 100 numbers like that. Or I could just take the number of times that I got the 34.9689 and multiply it by that, right? And then I could add that to the number of times that I got the 36.9659. Multiply that by, it was 24.23% of the time. 24.23% of the time. Let's see here. There we go. Multiply this by 24.23% of the time. And then I could divide all of that by 100, because it's like I pulled it out 100 times. 75.77 times gave me that. 24.23 gave me that. And then the answer to that problem there would be the number of, or the average atomic mass of my chlorine. Okay, you see that?
Yeah, I see it. So if you put that in your calculator and solve it, then what do you get?
Well, we get 35.45. Now, You should take your time and make sure that you can multiply here, add it to the product of this, divide it all by 100, and get that value out of your calculator. Okay? But we want to emphasize again, we took the mass, how many times it was drawn out of 100, added it to the other mass, and how many times it was drawn out of 100. Then we divided it by that 100. Right? We could have also set this up a slightly different way, and some people have been taught this in their previous chemistry class, where you take the mass of the 1, 34.968, and you multiply it by the fraction instead of the percentage, which is 0.7577. And then you add that to the mass of the other, 36.9659, and multiply it by, again, instead of the percentage, the fraction, 0.2423, right? And then you don't have to divide by 100. You could just think of it as only out of 1, because these are just a fraction of all of them. So you could divide by 1 if it made you kind of feel better. But the result there would also be the correct value. Okay? Very good. So, moving forward now. There are 2 isotopes of element Z. The first is 56.5% in abundance and has a mass of 152.3. And if the atomic mass is 155, what's the mass of the other isotope? So, how would we set this up?
Well, you would take the percentage of one, times it by the mass of one, add it to the percentage of the other, times it by the mass of the other, and divide by 100. But, so we got 56.5%.
All right, 56.5%. Multiplied by what?
152.3.
152.3. Add it to what?
I don't know the other percentage.
Well, it says there's only 2, right? So if I take 100 minus the 56.5%, that will give me my percentage of the other.
Oh, okay. What is that?
That's 43.5%. So 43.5%. And then, what is my mass of my second one?
It doesn't, well, what's 155.5? What does the mass, or the atomic mass mean?
That 155.5 is this number right here, right? The bottom number. Not for chromium, but just for whatever element it's talking about. So that is the average mass. So that is what this whole thing equals to, 155.5. Okay? So this is what we don't know, right?
Yeah, we don't know that.
So that's what we're trying to solve for. Okay? So can I solve for it just by having that problem right there?
Do you have to divide that by 100?
Yeah, I do. You need to divide that by 100 there, because it's out of 100 draws, out of the hat, right? Okay, good. Excellent work. So let's see if you can solve that and get, for your value, 159.7. Okay, see if your calculator you can get that. Work until you get it. All right, so here we have another scenario. An element has an atomic mass of 15.987. The mass of one of the isotopes is 15, and the mass of the other isotope is 16. What is the abundance of these two different elements, of these two different isotopes? Sorry. Isotope X and isotope Y. Well, if they were the same, abundance X and Y is the same, if they're half 15 and half 16, then what should the average be?
Well, if there's only 15 and 16, and they're half of each, then the average should be right in the middle, like 15.5.
That's right. But we're at 15.98, so what does that mean?
It means that we're mostly 16.
That's right. So that X is in more abundance than Y. Is that right?
X is in more... No, isotope X is 15.
Okay, yes. So X is in less abundance of Y.
Yeah, that's right.
Very good. C. Y is in more abundance because X is a smaller amount. Excellent job. Good work, Fred.
Thanks.